last talk, first I want to thank a dog to have me here. So wonderful to see. It's a very interesting talk. And since I have this board, maybe I should use some board too. So I'm talking about upwind. I do not, this upwind, I have some result, I have many open problems. I have the work I'm going to talk about relate to people sitting here. And first of all, talking about upwind, we look at the simple little problem, u double prime plus say u prime equal to 0, let's say u1 equal to 0, let's say u1, u0 equal to 1, u1 equal to 0. Let's take this problem. So you have this problem starting from 1. If you do the convection, somehow you hit the boundary, you go to 0 here. Okay, this is what the solution look like if epsilon is very, very small. And if you do that, the standard method, like a finite element, or in this case, you have this epsilon ui plus 1 minus 2 of ui plus ui minus 1 h squared plus this. If you do the central, if you do finite element, it's like a central finite difference. So this one, most people here know, but I just want to. In this case, if epsilon is much, much smaller than h, this one doesn't really count. So you have like pretty much ui plus 1 equal to ui minus 1. So that's, in this case, say you have what, say 1, x0, 2, 3, 4, 5. So your every other point is like 1. You have to have this point here like that here. Well, how many points? Like this one. But if you go this way, you have 0 here. So your solution going to be look like that. That's going to be numerical solution. So it's very oscillatory. So the upwind, you just look at this upwind in there. You have the same plus ui minus 1. So in this case, it's like ui equal to ui minus 1, pretty much. So in this case, you go, so this is oscillatory solution. The other one, you can pretty much go from here, you go down like that. That's pretty much the upwindian scheme. I guess the one of the things about upwindian scheme is that this one corresponds to the A of u equal to f. So A is AII is positive, AI minus is negative, non-positive, A inverse is, this is like M matrix property. The question is that we're talking about is that what if it's a finite element? Suppose a finite element, a multi-dimension, and unstructured grid. How do you do upwindian? So this is the things I'm trying to talk this afternoon a little bit. This talk a little bit, and so actually the motivation I do is this MHD problems, and MHD problem is the coupling between Navier-Stokes and the Maxwell equation. But in MHD, they have so-called reduced MHD. If you do a time discretization of that, there's something called a magnetic Reynolds number. I worked on this MHD, especially Kai Bo in the audience here. We wrote many papers on it. When we do the numerical computation with the magnetic Reynolds number is big, the numerical goes terrible. Something almost as bad as that one. And especially multi-dimensions. In this case, you have this curl, the Reynolds number inverse sitting here. You have this V, which is kind of velocity from the previous time step. You have situation like that. You do have this regularization term here, but I mean, this is a good sign term here for the time-dependent problem. So this would be good kind of this is convection dominated because V of m, Rm is big. So now what is upwind? I mean, I still have no clue, but I have some schemes. but all right. Wait a minute. Well, this is like a, well, I have a multi, if you think about is an approximation that usually the convection diffusion problem. You have this, you have this kind of a problem look like that. And what I'm doing here. What is this? Yeah. What is this? Okay, if you let's look at this problem here. Yeah, this is conservative form. This one is you can write it outside, but they are not the same equation. But in terms of operator, these are the kind of adjoint to each other. Okay, and I cannot handle both of these to appear at the same time. But you do either do this one or you do that one. Okay. So there are many type of methods doing these things. Now I'm thinking about upwinded. Okay, in the unstructured grid. You have you have a streamline diffusion and stuff like that. That doesn't count. Okay, but that's I'm trying to get some kind of M matrix or stuff like that. So the thing is, I'm actually start with this exponential fitting method. This U in this case is a gradient of phi. Wait a minute. Wait. Oh no. This beta is a gradient of psi. This comes from the semiconductor application. The nice thing is about this these things that you have this identity. If you do you can symmetrize these problems. You might introduce this variable. So based on this main change a variable, not in the computation, you could do a change of variable. Somehow it's not a good idea, maybe. But you there's again in your paper I read this part, but you also have this mixed part. But when I look at these things, the first question I ask is, what if this if this beta is not a gradient of something? In the general case, you just don't have it. So I have your paper is 1989, so I wrote a paper 10 years later, 1999. But I have 2 more 10 years work. This is 20 years ago. So how do we do this problem? So I'm going to extend. I don't know what's going on here. What is it? Let me see. So I want to consider flux. I'm going to do some derivation. Probably it's a little bit. I don't know. People still awake. I'm going to do some. So I look at the flux. Okay. So I'm going to pull this alpha out. I take the theta equal to. You pull this theta out. I'm sorry, I don't know. I probably should change it to another. Can I change it to this one? I'm sorry. I don't know why it doesn't work. And it's probably better, I hope. I'm sorry. So I do the idea. Oh, wait a minute. Now this should be alpha gradient U. I'm sorry. Alpha times gradient U. So the idea is that you pull this alpha out. The theta is like a beta divided by alpha. Okay, you have that terms. So the main idea in this talk is I'm going to somehow imagine I'm going to approximate this flux by a constant vector on the element. This is my starting point. But if it's a constant elements, we think about lowest order always. When you do the upwinding scheme, we always think about lowest order. So this constant vector can be written as a gradient of linear functions. Okay. So So if you do the integral by part, because it's in the divergence form, and we come to the Poisson equation. Okay. And my off-windier scheme is always based on the Poisson equation without any coefficients. So you write down out of the local stiffness matrix. That's how you write it, right? The local stiffness matrix. But the row sum of this local stiffness is equal to 0. You can regroup these things so that this is like a Wi minus Wj, Vi minus Vj. This is a negative Aijt. It's a simple identity. Okay. So what's good? So the thing is that this is the difference of a linear function is the tangential derivative. Okay. It's a tangential derivative along this edge. It's how it's tangential. This makes sense? This is the difference, okay? But we know this gradient W is J over T, but the thing is that Jt is supposed to be close to J. That's actually because this is just d theta u times tau e. So so far I haven't really done very much. The idea is that I reduce this volume these things to the edges. This is kind of the directional derivative on the edges, the tangential direction. So if we go to the next one, this is the one I just got. This is a tangential derivative. You know, if you look at these things, in 1D, you can always write on the edge. You can always write anything as a gradient, which is a derivative. You can take an anti-derivative, one dimension. I'm doing it on edge, okay? So this is like this is an antiderivative of theta, which is beta over alpha. So you can do this trick in 1D. Use your trick in 1D. 1D always true. So I put this together. So I put this one in there. I multiply this over. You get this, kind of approximate identity. So this is tangential derivative. I'm going to do the integration on the edge. I do the integration. This should be the edge integration. If you do these things, that's the difference between the point value at the vertices. You can also take the interpolation. Okay. With or without interpolation, it's just a difference. So if I do all the things, I'm going to just imagine this is my u. I become a uh. This will be identity. So I kind of approximate this u. This delta is just the difference, Wi minus Wj. You can somehow I replace it by this thing. That's my finite element solution. So in the end, so this one you do the integration, you divide over. So that's the equation I'm getting. That's my final difference scheme. Okay. And, that's my. And it turns out I'm going to show you later. This is going to be the M matrix property is the same as. Let me see. What did I say? Okay. The stiffness matrix is M matrix as long as the stiffness matrix for the Laplacian is M matrix, and independent of the coefficients. Your paper, you have to, because there's coefficients in each element, the variable coefficients, so you have to have the stiffness matrix locally M matrix when you put them together. Here, so the condition in this case, in that case, is non-obtuse triangle. This one is less over pi. Of course, the Donating triangulation is if and only if condition for 2D. Yeah. Oh, I wrote it here. AII is greater than AIJ. The diagonal matrix is positive, the off-diagonal non-positive. Actually, the inverse we were talking about during the dinner. I don't even know the precise definition, but what I'm thinking is the diagonal is positive. The non-diagonal is. No, the inverse. This positive means the positive interest, non-negative matrix. You can use issue is convection. There's some kind of diagonal dominance. They can use Neumann theorem to prove that. So I get the things. I'm going to come back to show you why this result is true. Okay. The thing is that in both 2D and 3D, as long as you're Laplacian, the linear finite element for the Laplacian is M matrix, then this one is also the M matrix. But it has it's a column sum equal to 0 in the interior point, but not the. So the monotonicity, because of in 2D, this is a 2D result. In 2D, the matrix is a M matrix if it's to any triangulation. For any coefficients. So we actually did some calculation. This boundary is very sharp. Okay, you just as sharp as you can imagine. But the thing that like in your paper originally, you're doing off-winding, but you don't really know. You don't really look at the directions. In this, if you have a negative sign, direction of the wind, which like in that case gradient psi. But you don't really, when you do the derivation, you don't really look at it. You don't really look at the direction. It's just pure mathematical manipulation. Yeah.
But this is related to Allen Southwell somehow.
Yeah.
Right?
Yeah.
Shuffle the gamma scheme.
Yes.
But did they do this general beta?
I don't know.
I'm sure not. But anyway. But anyway, it's all it's related. But I'm.
Just saying it's related, yes.
But you guys should know better.
Is there one differential?
Oh, it's an exponential fitting. Yeah.
So is this the two differential?
This is the 2D and the 3D.
Okay, this one I'm trying to understand.
But I reduce the sense to the edge. If you think about the stiffness matrix for the Poisson equation, you do this VIVJ. It's I and the J share the edge, which is tangential. That comes back to your 1D situation.
Yeah.
In 1D, everything is symmetrizable.
Yeah.
That's the trick.
Yeah.
Everything is graded. 1D, everything is graded. Now the question is that can I do this one? Okay, wow. This is actually. I first did the semi-Lagrangian. I put this, but I had a preprint. That's 10 years later, okay? 2009. But this, now I'm doing this 2019. Another 10 years, like this year. This is off-winding for this one, okay? I'm going to show you how I'm going to do it, okay? I call it simplex average finite element. If you do 0 form, which is gradient, you average on the edge. If you do the 1 form, the curl, you average on the surface. And do the 2 form, the divergence, somehow you get average on the volumes. But the thing is that you write this convection diffusion equation. I don't even know if I'm allowed to call this one convection diffusion or not for curl and the divergence. But let's call it that way. But, so you have all this, all this, what is dogs, you have this, exact sequence, you take the do, then you have this wedge things, the proxy, vector proxy of the, so this is kind of a model problem we're going to work on, okay. So now, so if you do so I call this one d theta, okay, so theta equal to, this should be theta equal to beta over alpha. So I'm actually had a conjecture, which all this for, I'm willing to conjecture is that for any alpha which is bound to be positive, okay. But there's no constraint on beta. This one should be uniquely solvable. That's my conjecture. I don't know if there's a PD expert here, but okay, you can prove it for D. If for 0 form, you can prove this one. That is true. Well, except Franco, I still, you're not, you're skeptical on that one. But anyway, I checked it again last night. Seems to be okay. It's not written in many places. Maybe but it's in my notes. If this one is actually a gradient per psi, it's also true. The reason is that you have this. If this one is the gradient per psi, this is also well-posed. But my conjecture is that it should be well-posed for any beta. Huh? Oh, yeah, maybe yes. Put some smoothness if you don't feel comfortable. Well, you do integral by part, you know. You go the beta is not going to be. Yeah, put a C1. Okay, that's. I think that is probably enough, but let's make it continuous. But anyway, it is whether beta is a gradient of some, or the divergence beta should be 0 or not, stuff like that. Whether or divergence beta should be non-negative, that's kind of more relevant question. They're all relevant, but those I think the weakly maximum principle, it does hold for any infinity. Yes, maybe C. Yeah. But no. If W1 infinity, if you do W1 infinity, yeah, that it makes it a little bit more comfortable. But you still don't know for sure if this one is well-posed, because beta. If beta is it's beta divided by alpha is gradient of something, this is well-posed. So the thing is that you have your trick in your paper that if it's a gradient, this is identity. But it turns out if it's a curl D, it's also an identity. We were excited, you know, a paper we call a magic identity, but somehow it's just trivially true. But we just got lucky. I don't know. We didn't know. I don't know. Okay, this identity is just true. Okay, for if you do this one here, you can take a theta equal to psi theta dot x is a linear function, or take the general gradient psi. Lots of typos. This one is what you did in your Franco Donatello's paper. If you do curl, this is also true. Okay. If you do div, that's also true. But you just have to do the proxy theta. Yeah. So if you go back. Yeah.
And you're always thinking beta to be a 1 form. Why not also consider beta?
Beta is no. This beta, I'm sorry, this is all different. This beta is this is a 0 form, right? This just this is a 1 form. This one is a 1 form. But anyway, it's just this. Yeah.
You might be able to get even some more by squaring the form degree of theta.
Oh, okay. Okay, that's a good point. I have to. Yeah, if theta is a gradient of phi, you can do these things. So you can make a change a variable. You get a symmetrical positive definite problem. So that problem is well-posed. Okay, and but my conjecture is that this should be true for any alpha and beta. Would you ask me why? But anyway, I have many. I don't have a good explanation, but except that. Okay, I'm doing this lowest order. Okay, for this thing, with the Alpha-Indian scheme. This what you have all this commutative diagrams or stuff like that. Now, let's see if we can do a curl. I'm going to do the curl. I write this same thing. Okay, I write this as I pull this one out. This I call that theta. So this one equal to that. I also still make that as an assumption, okay, on the things like a constant. I approximate the flux as a constant. And so if it's a constant, I can write as a curl of something in the edge element. Am I right? Okay. But so you do the same trick. Now you do this. I come back. Originally I have the Laplace, and this one is like the symmetrical problems. Okay. So an identity we want to do in this case, you take all these faces that are different. This you can write the stiffness matrix by manipulating with this this basis function of the edge element. Okay, it's lowest order. Okay, so this delta f would be just this curl. You use the Stokes theorem. That's the delta f. If you think about in 1D, it's a Stokes theorem for 1D. It's the difference. Okay, and so it all works out in terms of this FEC. Like, I think, Doug, you're running this things here, so I talk about this, okay? But the structure, whatever. Now I do the same things. You do this. Wait a minute. You do this guy here. Oh no. This guy is what? This delta f is delta. This one by definition. Okay, this is because of this one. Delta f is this y, because this one is actually going to be the curl is actually constant. It's the lowest order. So it's multiplied by f equal to that. This one is don't forget that this gradient is actually my original is a constant approximation of the flux. Okay. So that one is actually going to be close to the j. But again, I pull this one out. I have this same thing as I did before, except this time I do it on the face, not on the edge. When you do the gradient things, you do things on the edges. And this time I do the face. So I have this is the things I just did. This is the delta f. You are close to that. So now I'm going to use the identity. Or if you say that equal to, you can symmetrize it. But the problem is that I don't have that luxury. I don't have that. So this is I make another, but this one is not true. Here I make another. I'm going to assume I'm going to just introduce another approximation. On the face, I do some kind of constant approximation, let's say, average or stuff. It's a constant vector. The constant vector can be written as a gradient of psi, which is this one dot by x. So this one becomes a symmetrizable. If the symmetrizable can do the same trick, so that's what I did. I'm going to integrate by integrate on both sides. In this case, if you do these things, you do the Stokes theorem, it comes to things on the boundary. That would be the you can put interpolation here, or you don't have to, but it's the things on the boundary. You can also do this, put the interpolation here, But so you have this inequality identity. This is the delta, the WH comes from this constant approximation of the flux of things. You do this. You still do harmonic average. You get all these things. This is what I call the simplex average finite element method. Okay, let me just recapture what I did. For the gradient case, you do this and reduce everything to the edges. It's the difference between this edge. In this curl things, you do the things on the surface, the face on the boundary. And then I do the average on those lower dimensional simplex. But unfortunately, on that case, I cannot quite make the symmetrization. I introduce an approximation. So the interesting thing is the following. If you go back to when I had it before, okay. Actually, I'm just trying to tell you, there's a very interesting fact is that I have this WET there, you know. The WET, when you do the finite element assembly, this I and j, if you do Aij, meaning really is the vertex I to vertex j is connected with an edge. If this is the shells around, basically if you sum all this up, because I did that only one element, if you sum it up, you actually get this global stiffness matrix entry. Okay, this one. I sum this with all the edges. Okay. So this is the entries, each edge, which is an Aij, E is like Aij. So it's the entry from the global stiffness matrix for the Poisson. Okay, this is important. For the Laplacian equation, from here you can see very quickly this scheme has the same M matrix property as the Laplacian. the discrete Laplacian for linear elements, regardless the. Oh, I'm sorry. My coefficients has to be continuous. Otherwise, if you have a jump, you do the average here. Yeah, but that's a different kind of thing. But for this one, have this statement to be true, my coefficients should be continuous. Huh? For upwind, yeah. If otherwise, you have to do the local guy. You have to do with that. You do this one. You do the non-obtuse triangles. If the local is image, you can always put together is the image. For the interesting thing is that for the curl problem is that you also get this. If you take a f prime, if you take a two faces you intersect as an edge, that's the degree of freedom of the edge element, right? That's one degree of freedom edge. So you can also get the global simplest matrix when you assemble these things. Somehow you do some harmonic average of the coefficients. Somehow I was doing these things in the last couple of days. Somehow I do not quite get a neat formula for these div things, but to assemble them together. But nevertheless, you still have some sort of upwindian scheme. I do not know what I mean by upwindian. I just except that, okay, let me show you some numerics. When I plug this in all these crazy coefficients, it's always a sharp boundary layer. But you see, in this, there's no maximum principle for the curl guy. For the div, you don't have maximum principle. I don't know, maybe there is something there. But if this is a standard finite element, edge element, or this is a div thing, because I think in 2D you do div, in 3D it's lots of computation. But you do the div things, you get a sharp boundary layer. All the calculation were done. It's still a mystery why these things work so well. I say, for the gradient, I know. I get an upwind. I get an A matrix. Regardless the direction of your flow, just automatically get an upwind because of this exponential fitting business. Well, this is a stretch, the statement I'm going to make here. This U of H, it's kind of more or less look like some kind of interpolation for this positive definite problem solution. This is not quite true, but it's very close. And so you kind of not deviate very much from the solution of symmetrical positive definite problem. Upwind, I don't know. But I struggle because I have to give this talk. I have my post. Okay, Shounan, by the way, is the co-author. He did most of the work here. But I've been trying to. He gave his talk a totally different way, but I'm going to. I rewrote it. But I'm trying to make sense out of it. I don't know what is the upwind. There must be some kind of physics. I need your help, dog. You're the curl deep business. But for the gradient, maybe there's some kind of physics. I think there's also Lie derivative, Lie convection. There's a certain notion of convection, but we have not got around to get into that. But it just works so well. So there's some underlying mathematical structure. So so we want to do analysis. Actually, another thing we want to do preconditioner, and to solve this non-symmetrical problem with convection dominance is not a pleasant task. You talk about precondition. That's what I do for a living, So you have this commutative diagram. I call it gradient theta. This convection term. I call it gradient theta, curl theta, div theta. If you put this E theta, which is exponential theta x, or maybe you can do a gradient phi if you wish, and this all commute. Okay, if you have this, I'm going to introduce a convective derivative, okay, and I call it gradient theta. This is still this is commutative diagrams. Okay, this is kind of the mathematics, one piece of mathematics. Now this is a continuous level. How do you do the discrete level? The D-square level, you just, you know, you do use Douglas notation, you do all this stuff. Or you still do these things, you do the interpolation for this E of theta exponential guy. And, but you need to somehow to do the discrete version of this gradient theta. If you do that, you know, you just make this one commutative, you figure out you need some stuff. So you get all these things. One of the important things is this guy. Somehow this is some kind of interpolation which keep all this commutativity, all this discrete structure for the things that, for all this theta, but for the zero form is the original interpolation. For the one form and two form, it depends on the coefficient. So with these things, you have all this complicated, all this commutative diagram. But here you have no, in the back, there's no, wait a minute, in the front, some part is, I even got dizzy myself. But there's the one without theta, the one with theta, then the one without h, the one is continuous, discontinuous. You put all this together, you have everything commutes, which is nice. But to do these things, I need to prove this in-soup condition. Actually, using this commutative diagram, you can actually prove the in-soup condition. Okay. Oh, okay. In this case, it's no convection dominance. I just want a convection diffusion problem. And for purely convection dominant problem, you want to say this one's a uniform. Nobody knows how to do this business. But if it's just convection diffusion problem, you can prove H is sufficient small. You have in-soup condition. You have all this rate of convergence and all that. The numerical, I did the experiment. Actually, I didn't do it. Shounan did it. You know, you do the error estimate. You check. They look good. But if alpha getting smaller, you want to let H to be small enough to see the order of convergence. What is these things? Is it HD? I did that before. I think I did that probably earlier. Huh? U1 because I cannot plot a vector. It's U1, U2. I just take the first component of the solution. Is there any way to plot a vector? But huh? Okay. Yeah, that's right. Okay, I have to do this level set also. But anyway, I do this is just take the first component. I can let this alpha go to 0. You know, get a very very small. You still preserve these things. These are magnetic random sum go to infinity. The things actually stay pretty good. The 3D conversion problems, again, the rate of convergence is still okay. In this small, if diffusion dominant, if it's conversion not so dominant, you see the rate of convergence very quickly. but this one it catches up when h getting smaller. Okay, that's also solver. So if you do the convection dominant, if you do UPWIND scheme, you get an M matrix. You know, you can do different solvers. Actually, I probably still like the things I did many years ago. You can do AMG with agglomeration graph partition, but you actually do the very simple aggregation and do piecewise constant basically. In that case, you can preserve the M matrix property on the coarse mesh. If you do fancy prolongation or restriction, you don't. But anyway, I can tell you that for M matrix property, I have very efficient multivariate solvers. Okay, but you have to do a good smoother. You do the Tajang smoother. You have to somehow figure out the flow direction. The Gauss that works like a charm. But if you cannot quite do that, we have all kinds of tricks. But in the end, solving the gradient convection diffusion problem with the correct discretization is a reasonable thing to do. Okay, so I cannot claim I can solve all the cases, but you can even prove some theorem. Now the question is that can we use this? So we some years ago I did with Hiptmeyer. We solved this curl these things by using the Laplacian. Okay. Now the question is that can I use this what I call H gradient theta? Okay, this by notation, but I just show you that for this convection for the zero form, I use that solve as a precondition. Okay. So it turns out we can do that. So the thing is that when you do the use the H1 elements to do the H curl, H1 in the continuous case is a subspace of H curl, but not in the discrete case. You have to do an interpolation. That's the here, but the interpolation here we have to use this convective interpolation, which I derived by all these different commutative diagrams. So there's a very sophisticated, I don't know if it's a complicated procedure to get there. Well, it's not complicated after you have done it. But you use this kind of interpolation which depends on these convections. If you use study interpolation, it works like a charm, okay? It's just we have no theorem yet. You need to prove these things. You use this as precondition, use GMRS. Again, I start from the convection diffusion proof of the gradient. In that case, the M matrix. M matrix, for example, Gauss-Seidel always converge. And if you use Gauss-Seidel smoother, if you follow certain directions, usually it works very well. Otherwise, you introduce some kind of cross match, you do aggregation, and use some very simple kind of M matrix structure preserving. Use the M matrix probably should preserve. You go to the cross match. You can only do very simple and kind of easy one, just like a piecewise constant kind of approximation. So this one kind of works pretty well. And but if you don't do this non-symmetrical one, it doesn't work. This slide pretty much tells you that. Now if you do MHD, use the convection. Well, this is what I did like 10 years ago, but still I wasn't terribly happy. But now I think with these things, Shounan did most of these things. He claims that I had some issues before he claimed he could do it. Actually, to be frank, I haven't talked to him about this one yet. I use and he said there are many things he could do by using this type of method. You can even do some theorem, solvers, all that. So I struggled. Kai Bo, and when he was doing his PhD, we wrote several papers. Mostly he, did all this work. But that will assume the magnetic Reynolds number is reasonably small. But here, that's pretty much how I got motivated. Because I got a Shounan, he was a postdoc in Penn State some years ago. Then I said, okay, we got to work on this one. And but he's a great programmer. He really can code. Well, he proved theorems. But he coded many of these things. It works very well. Okay, I think I'm down here. I'm just saying that this exponential fitting somehow does the upwinding job. Is the windy. But gradient, if you do the gradient kind of things, you approximate the flux by some constant. You reduce the Poisson equation. You reduce to the edges. So for the edges, everything is symmetrizable. So that's how I got around with this edge average. When you do the surface, you do the curl. You do the things. You have to do things on the surface. That case, I cannot quite do it, so I have to do some constant approximation. It turns out it works very well. The interesting thing is that after you assemble this together, these coefficients of these things depend on this global stiffness matrix of this corresponding Poisson, Laplacian, graph Laplacian, what do you call those things? how do you, no, you don't even have the other term. How do you call this one? curl. And it just corresponds to the coefficients from there, which I find is very interesting. And that's making it the more, this matrix property is more, is true for more general mesh. Otherwise, you have to only work on this mesh. So it does use some flavor of exterior calculus. Somehow we make some use of it. But the convergence analysis, somehow we need, there might be other way to do it, but sure, I'm working out all this commutative diagram he loves, but I find it too complicated. But he did all this proof, and especially this precondition which I did with Hypnite, he put that interpolation there, and it works very well, which I find is very, still no proof quite yet, but numerically it works very well. Okay, that's it. Thank you. Yeah.
So both the preconditioner and the method have the exponential fitting, right? In your last example.
I have all the algorithms. Yes. But the interpolation, one of the main things, if I don't use the exponential fitting, use the Laplace, it won't work. But the interpolation operator, which from all this commutative diagram, somehow makes it work. If you change it to the regular guy, it doesn't work.
I have a question.
Yeah.
I'm not sure I quite followed your exponential fitting. I mean, I didn't see it.
Which
How
one?
do you use it? Go back to the first convection diffusion.
I don't fit anything. I just, you use that terminology. I don't know what the exponential fitting actually means. I'm sorry. But because that's how you guys call it.
Use that terminology because we've got an exponential.
No, you have an exponential function everywhere. I don't know what to call exponential fitting. I suppose when you do the boundary layer things, you take the exponential, but that has nothing to do with this boundary layer exponential fitting. I use exponential fitting because it's in your title of your paper. Because actually, so I don't like this, but Shounan, my co-author, likes that. He wants to call it. But okay, I mean, this is all the scheme, you know. Maybe look at look at this thing. Maybe I do this gradient case.
Yeah.
The gradient case,
The H1.
yeah, the H1 case. The H1 case, because you do the integration factor, right, into 1D case. You do the antiderivative of this guy here in 1D. This is basically pretty much the integration factor, which should be exponential. Do you want to call a fitting of that guy?
No, I didn't follow the steps.
It's the same step you did, but except I did on the edge. You did in the whole volume.
Okay, because the transport was a gradient.
Yeah, but here I do the edge is always a gradient.
Oh, okay.
When doing in 2 dimensions, it's kind of exponential fitting. We had to be careful when if the gradient of psi was really bit too big, I mean phi was far away from the constant, then the explanation.
Yeah, this one, this is something you have to use this Bernoulli. You have to use the Bernoulli functions.
Rescaling of the matrix.
Now this Bernoulli function b of t, t of e of t minus 1. You have to write a code to, when t goes to infinity, this things go to 0. T go to the negative, when it looks like a t. T go to 0. You got like a 1. This is something. This is the ultimately. Yeah, you just write a subroutine. No, you just write a subroutine for this guy. Yeah. If you do not put this together, your code always explodes. Because I got maybe 3 students from the last 20 years that did this. Every one of them would get a very bad solution to begin with. I didn't tell them the trick, but one of them failed in the beginning. Everyone got a lousy solution for the problem you said. But if you do these things, then you don't have that problem. The numerical, this is very important, very critical. Okay, thank you.